So, good morning. Hope you had some nice Easter holidays, enjoying some of the warm weather. Today we are continuing with analyzing objects and two specific types I'm going to focus on. And well, the literature I think you essentially know already. And then there is a collection of papers. And yeah, I think actually I should update them because they are getting a bit old, but still valid. And what we have done until now, we have looked at different steps in the process, and we are getting closer to quantifying information from our data. So we started out doing image enhancement, then looking at histograms and trying to do segmentation, identifying different regions in the images, taking one step further, identifying individuals within these segmented areas. Then on top of that, doing analysis on each shape. And we looked a bit on the complicated shapes. We're using the thickness map or combination thickness map, distance map. And that is where we are to take it up now. And we have a couple of things that we want to look at. And the first thing we are going to, well, first a little bit the motivation, and then we have skeletons, minimal structures of our items. And the other one is watershed segmentation, to look at the labeling of items that touch each other. And that was a thing we saw with the component labeling, that it didn't work. So that these are the two main things we are going to look at today. So we have some different metrics. We can look at our images, we can look at it globally, we can look at it locally, depending on what we want to see. And different types of operations. Some we do on single points and some we do on the voxels, looking at neighborhoods, how we can do some tessellation, doing triangulations, etc. And even looking at some kind of correlation function between 2 points that was relevant for the texture analysis. So we have some matrix beyond just looking at the items themselves, where we had all the region properties. And now we want to look into topology of a structure. And the question is how we can extract this information from the images. And another thing is how we can separate different objects, even when they are close to each other. So you can't resolve either you can't resolve or they are actually touching each other. And we can also see what happens with the shape when they start growing. And here we have an example we used last week, or no, 2 weeks ago. We looked at the distance map where we had this segmentation. We looked at some foreground distance, where you can see that there are some peaks in these regions. Or we can look out away from the objects, and then you can see the greatest distance or the midway distance between two objects. So this is one kind of information we can look at. It doesn't really always bring us all the way to what we want to do. So for example, we can, if we want to look at some distribution, we may want to see how many cells are alive in a microscopic image. And for that we need some criteria. So one would be, for example, that we have small cells are dead and larger cells are alive. Then we would look at the size distribution between these cells, which would be easy if they are well distributed, but they usually cluster together, so it's not so easy. Can also look at shape properties, and that living cells are more round, swelling, while the dead cells are shrinking and more irregular. And then we can look at, for example, anisotropy or ratio between perimeter and area, things like that. We can also see, look at positions or look at colors. And for the counting, we can also look at how different colonies are growing. So you can see, so if you separate the image into different segments, you can count how many there are in each box, and then tell that these regions, they are probably better fed than other regions. And then we need some statistical methods to compare between these, but that is actually next week's lecture. And what we still need to do this is a way to counting the cells, so we need to find them. And then afterwards we can look at, once we have them, we need to know where they are, and then we can see where are the closest neighbors. Again, we come back to the region properties, where you can compute the centroids. And then we can look at different metrics based on the distance from each cell. So now we want a tool that can do all this, and ideally which is also adaptable, because you may have one question this week, but next week you want to something else, and then it should be easy to adapt your workflow, that you don't have to rewrite, I don't know how many lines of code, but it should be designed in a way that you can use it for further analysis. The thing about coding and how to organize your workflow is something I come to in some weeks in one of the lectures. Must be in 2 or 3 weeks, I think. And so now we have an idea about say overarching things that we want to know. And until now, we have already been able to measure these things. We have the area, perimeter, orientations, positions, and so on. And today, we are now looking at 2 more structure analyses, and these are the skeletons and the advanced object labeling. Skeletons. So we have a lot of structures in our images. Depending on the application, you can see here, going on different scales, we have roads and streets on an aerial picture. You have rivers, and if you go below the soil, then we can look at root structures and root networks. And in medicine, we can look at blood vessel networks. And all these have in common that they have very thin structures that are branching and in principle behaving from an, say, abstract point of view in a similar way. Some may produce loops, other not. So on the streets map, you definitely have loops, because every city block is a loop. Also the rivers, if you have an island in the river, then that's also a loop. When you come to roots and blood vessels, they should be quite loop-free. If you have loops, it's more because the image cannot see the difference between crossing lines and not. So these are different from those in the kind of structure. And things we would like to know is how these networks are connected, how much they are branching, if there are loops. And to do this, we want to look at simpler metrics. One is the tortuosity, which I'm going to talk about later, and also branching, how often and how many times do each point branch. And these can be metrics that describe the topology of your network. And a very simple example, reducing this horse to its skeleton. It's not its true skeleton, but it is the minimal structure that spans up this horse image. And that is what we are aiming for in this case. And if you look at it, for example, the main body is just a thin line, but it actually captures the ears and the little irregularities back here on the tail, and that is also branched out here in some kind of branched network. But in primitive sense, this is a horse. So that is the idea of the skeleton. And looking at a more practical example, we have here a little piece of a street. So we have an aerial image of this street with some different side streets going in different directions. And we want to analyze this street network here. This is still very simple. But anyway, it's a matter of space and level of detail that I'm reducing into this. So we make it even smaller just for the analysis now, or for the demonstration. So I'm taking this little area here in the middle and crop that. And then we still have just a main street and 2 branches. And this is what we want to see in our analysis. And let's see how far we get. There is a little bit of code here. In principle, it is for the cropping. So you have the cropping of the image to get the small image, and the street points that we have here as a ground truth, they also need to be extracted, and for that we're using this query function. And then we copy out and remove some bias, because otherwise the coordinates would be on the wrong place. The first step we need to do is to segment this picture. And it's a color image, so we need to somehow make it easier to segment. Now we take a very simple way. We just do the RGB. This is represented in red, green, blue color mapping. And we convert it into hue, saturation, value, color mapping. And with that, we get essentially the gray level image out of it. And the gray level image, we just put a threshold, choose an arbitrary one in this case, without looking at any histogram, but ideally we should use maybe some of these segmentation algorithms, but here we stay with something easy. Then, as we have some misclassifications, do some opening, and this is the result, which looks a bit messy, to be honest. So we need to clean it out. And let's see. Yeah, well, of course, we can do other things. We could use some k-means. We could use k-nearest neighbor. We could use the color space in to make it more precise, because if you look here at the picture, the street is more some kind of gray-brown color, and things outside, they're more green, except for the house roofs. So we could probably do something smarter, but this is just to get something to start with. Now we want to identify the street, and the street in this case is the largest object. So what we do is we label the image, so we get these colored patches, and we can see that label 1 is the largest, so this is what we're going to extract. And doing so, yeah, we can, so that was apparently here the last pass. But anyway, we will extract this one label later for the analysis. So, skeletonization, there are different ways to approach it, and one is to look at a distance map, because when you compute the distance map of this structure, let's see, that one, yeah, that should have been on the previous page. So let's look at the distance map we can see that you have in the middle a ridge, because everything is always going up from the edges, building this ridge. So that could be a way to identify the skeleton. And we could apply the Sobel filter to it, and that would, no, Laplacian, sorry, to it, and that would look like this. And if we do that, we see already that we have a very strong structure on the top, but there are also some interesting side edges, so this will be a quite messy skeleton if we start looking at it, because it spans up every little bulge on this structure that we segmented, and that's a bit too much. And from this, if we want to do a skeleton, we can look at two different things. We can look at the distance itself. It must be a greater distance than some threshold. And we can also look at the minimum slope of the distance, saying that the slope must be some value. And looking at the bivariate histogram of distance and Laplacian of distance, we would say with these criteria that pixels that fall into this region will be defined as our skeleton. And the resulting skeleton, I didn't pay attention to where the slides came, but here we have it. And so you see the Laplacian of distance, and if we do the extraction as using this double thresholding approach on the two variables, then you get this skeleton, and kind of looks like the street, but there is a lot too much information on it. There are also other approaches. This is, I would say, was the one of the first people did. But today the algorithms are more talking about morphological thinning, which is in principle that you erode until the structure stabilizes. And stabilizes means there are only one single pixel or very minimalized pixel structure. So you can iterate until you get the skeleton. Still, there are some junk branches, but much less than we had before. And there are two different approaches. So one is the morphological thinning, which would be the iteration. And then we can also do some pre-processing before we start doing our analysis, and that would be opening. And then when we do thinning until stability, we get that skeleton. And that is what we're going to work with from now on. So let's see, where would you have it? Yeah, so there is this medial axis, which is the one that I recommend that you use. But depending on your application, sometimes thinning is the right one, sometimes medial axis. So you have to explore which one is the better alternative. Then now with the skeleton, we only have, again, a bi-level image. It doesn't say much about the topology or how it's built up. So we need to do something more for the analysis. And one way to do it is to apply a box filter to the skeleton. And the effect is, first of all, that it's getting wider. So we have a box here, 3 by 3. And it's getting a little bit thicker, which we didn't intend. But by just masking the skeleton pixels, we get this skeleton again. And now the light is not ideal, but you can see that the major part is this green yellowish, but out at the endpoint it's blue, and you probably have to see that on your own screens, but there are some gray points also at every junction. So what is happening now? Why do we get this? Here you can see it a little bit in close-up. Here it's easier to see. So what is happening is when you apply this convolution kernel, it sums up all the pixels in the neighborhood around the central pixel. And if you have a straight line and look at, for example, this little, so look at this point here, look at the 8 neighbors, you can see that you actually have 3 pixels within this little region. So that is why we get the 3 here. If you look at that one, you can see that in the 3x3 region, you have 4 pixels, so that is the value. So it's actually characterizing, with this convolution, you're characterizing how the local topology is. And the last example is the 2 here. So at an endpoint, it only has 1 pixel coming in and the central pixel, and then you have this value. This is a very clean skeleton example. Sometimes you can have, depending on the algorithm, you can have additional points in the corners, which can be a bit confusing. So you can interpret those as 5-way or some kind of, in principle, a 5-way crossing, or you can just say that it's a thick 3-way. Depends on how you want to interpret it. So now we can look at the different constellations. So we know that 0, then there is nothing to sum at all, so that is background. A 1 is an isolated point, so in principle, most likely some kind of misclassified pixel. Then we have the 2, which is an endpoint. 3 is a line segment, doesn't matter in which direction. Then the 4 is a 3-way junction, and the 5 is a 4-way junction. And now we can run this on this image, and we can see that we have neighbor count equal 2. Then we can see just all the endpoints of the skeleton. Neighborhood count 3 is all the line segments, so that's the main body of the skeleton. Then we have neighbor count 4, then you get all the junctions between these, and 5, there is no 5 right here, not visible at least. That could have happened, but I think actually if with higher detail, I think we would get something around here. That should be a 5, but we didn't get any. So this was by summing just the same with a uniform 3x3 kernel. We can also do some smarter coding to get more information about orientations of the branching. And if the kernel is defined like these two, we can get even more information, because now we can tell in which order things are coming. And the reason for having this is that these are the binary numbers. So we have each position in the binary number will be filled up if a pixel matches these positions. And 256 is just to mark out the central pixel. And the is that 0 is of course the background. If you have something that is less than 256, then it's a pixel that is touching the skeleton but is not on the skeleton. And everything that is greater than 256 is on the skeleton and has its coding. And then with some lookup tables, you can do the analysis of what the meaning of this. And you can see here that it's actually going clockwise around here, and this one is also going clockwise. And looking at the different codings, what they look like, we have the 3x3 box, we have the J4 that I called it, and the J8, and you can see that the numbers are much greater, and so the values of the numbers are increasing when you go to the right here. Which one you use is again depends on your application and what you want to do, but you have to just decide, explore and decide what level of detail you really need. The analysis can be much more complicated if you have this kind of coding, but on the other side, you can also tell more about your structure. As you saw here, there are a lot of strange sidelines, and this is actually not part of the true skeleton that you would like to have. So now we go into the prune. Yes?
Using such a kernel, wouldn't it make it sensitive to the direction of the structure we are trying to analyze?
Pardon? This
Like this kernel which uses like 1248.
yeah, yeah.
Wouldn't it make it more sensitive to the direction of the structure? Like if the skeleton is like horizontal instead of vertical, it could be different.
Yes. This one, these two, they sense directions, also orientation of the lines, and also of the branching. So, for example, if you have a fork going up, then it would be the sum of 1, 4, and 32. If you have fork going down, it's 2, 64, 16. So you can really tell the orientation on how the skeleton is, or the different structures in the skeleton are.
My only concern is that wouldn't it be less adaptable to different structures then?
Why? This is all information you can get about. So it's more about your interpretation of these values. How you interpret, that can be sensitive to the real structures. But if you don't want any... No, wait, I'm going the wrong way. If you don't want any orientation information, then you go for the 3x3. Then you have it more generalized. It's just a junction, or it's just an endpoint. But if you want to know the endpoint is pointing up or pointing down, then you need the other type. So that is what I was saying. It depends on your application what you really need. Yeah. Let's see. There I see. So I was now at that we have a lot of branches, and we want to prune them. And the way to do is, first of all, we may have to use some kind of model maybe that decides that what is relevant as to remove or not. And things you can look at are minimum branch length. Let's say you look at all the line segments, so that would be count 3 in the box coding. Then you get all the line segments, and then you can tell something about them, and counting the pixel for each segment. Or you can also look at the branch width. In that case, you need to support with the distance map value as well, so then you need that as additional information. So the first step is to analyze the branch length, is to label all the segments in the lines. So that would be first extracting the number 3, and then apply a component labeling. And here the component labeling is no problem because nothing is touching. So we have removed all touching points. And then you can see, if you compute a histogram of this, you can see the distribution of the segment length. And let's say we don't want length less than 10. Then we sort out all the small branches that we have. This can of course also be plotted, so you can see the segment length as a color code, gives you a visual feedback. And then let's look at the pruned skeleton. So we look at the length skeleton where the length is greater than 5, and looking for all the endpoints and the junctions, and that is what we get then. Now you can see that all there are a lot of endpoints outside. We may have to prune them as well, but well, this was probably some kind of mini branching. But the skeleton has improved a bit more. Still, we have some, compared to ground truth, we still have some branches that we don't want. But the skeleton is quite sensitive really to small fluctuations on the surface. Every little fluctuation create a new branch. So to do a skeleton, it's good to have a very straight surface line of these objects. So that could be seen as some kind of first criteria. Another way to look at it is the maximum width of the skeleton. And for that we need to use the distance map, which was computed a bit earlier. And then we map that to the skeleton. In this case, we look at the maximum distance. So we are not looking per pixel at the distance, but the maximum distance or thickness of that segment is used in this mapping. And then we can again see that there are some that are very narrow, and the major part is more than 5 pixels wide. Or actually, radius 5 pixels. And some, they're really going up into really fat structures. And then looking at the pruning with the width, it actually gets a bit cleaner than the one before. So we're getting something that looks even more like the original skeleton. And just as a comparison, this was the original skeleton that we used. Now from having this skeleton, we can look at different topology. We have already seen that we have the segments, we have the junctions, we have the endpoints, which tell something. But if we want to go beyond that, we can, so here is a plot of where we have them, just to display it on the picture itself. But now we want to get more idea how are these elements of the skeleton connected. So now we want to really see how a more abstract notation, and for that we look at first a little very simple image or network. We have 2 nodes, one here, and 2 edges here and here. And in the analysis, we start with just segmenting and labeling nodes and segments or edge labels. And they turn into 1 and 2 here. And here we have the edge labels, also 1 and 2. And now we want to see which nodes are connected to each edge. And to do that, we use a dilation operation from the morphology and code for that. So we are actually creating this image. We label the different parts and apply the dilation to first labels of 1 and then labels of 2. And the result of that analysis is first we have the nodes, and they get labeled. And when we first grow node 1, we get this blob here. Then we want to see which edges are actually overlapping or in contact with this block here. And if we look at the edges here, we have them, these 2, and we have them labeled here. And then we can see that this one overlaps only with the edge label, which is 1. If we now do the dilation on this node, we see that it covers this whole block here. And if we look at the overlap, it actually connects with both 1 and 2. And with that, we can see that we have a connectivity. We can create a connectivity graph, and that is maybe in this small example not so clear. But if we want to run, we can analyze the street into these different points, but also how to work with them, these pixel counts. So we see here that the endpoint is a node. We also see that the different junctions are nodes, while the pixel count 3 is an edge. So this way we can separate our skeleton into these categories. And First, we want to identify where we have our nodes. So they are spread out over the network here. Here's a bit of code how to do the bookkeeping. So every node gets an X and Y position and also a width connected with it. And then comes even more bookkeeping and running through here in this code. I'm not going to do it step by step, but what it does, it is identifies with the help of this dilation approach, it identifies which edges are connected with which nodes. And here you see edge 1 connects to node 1 and 2, edge 2 connects to 2 and 3. Then you can see here that edge 3 and 4 connect actually to two different, they have something in common here with a 5, and actually edge 5 also has that, so it's a multi-way joint. So let's look at these segments and do some measurements on them. That was also in the previous code, but now I tableize it. So we have start and end points of each segment. You see some of them are quite short. So this starts at 26 and ends at 27, while others are a bit longer. No, most are actually just between 1 and 2 pixels long. Then you can see, no, that's the node numbers. Okay. And here you can see the length, and you can also see the Euclidean distance. The length is counting the pixels for each segment, and the Euclidean distance is the distance between start point and end point. And further information that we measure is the maximum width and the average width. So all this information we collected in this code. And from this, we can start doing even more analysis. So one is looking at how the node networks looks like. This one is now the width of the line is connected to the actual width of that segment. So you can see that some of the segments, they were very thin, while others are more fat. And you can do this coding and get a better overview of how the network looks like. This connectivity matrix tells how the pixels items along the diagonal with which ones they are connected with, and the intensity tells, in this case, I think it was the average thickness of that element. But you can put any information. You can put the length, you can put the thickness, you can put tortuosity, which I'm coming to in the next. And tortuosity is a ratio between the distance between start and end point and the length of the segment. So this one has a low tortuosity, essentially approaching 1, while this one has a much greater tortuosity. And there is a nice description further on tortuosity on Wikipedia. And the reason why we want to know it is, for example, in geology simulations, water flow through porous media, it's good to know how fast you can expect the fluid transport to go through a medium. And then it's not only single position or single channel tortuosity, but some more average tortuosity of the whole system. Also, in chemistry, you can also use it for some size exclusion. In vascular tissue, can also be relevant to look at. If you remember the picture I had of the blood vessels, they were quite curvy and twirling around. So depending on how the blood vessels are organized or looking like, you can tell something about the health status of that patient. Then we look at the street map, and we get here some, That one is not updated. Okay, so the transparency of these lines should tell the tortuosity, but right now it wasn't updated. And here you can see the tortuosity, and if you really pay attention, you can see that the values here are between 0.3 and 0.9, and before I said it should be actually greater than 1. The reason is that the start and end points here are always excluded from the curve measurement. So if we have, let's see if we can draw it. We have the start point and it does something, and then we have the end point. That one is not included in the length of the curve calculation, and that's why we get values less than 1. And also the segments are quite straight lines. So that is the reason why we have these lower values. And then with some network plotting tools, we can actually plot this kind of, let me see if I can, oops. Now it's hidden. Yeah, so there it is. Yeah, so there are some tools to draw these networks. So this randomly organized graph is, if you have a very long line, this random graph tries to compress it and make it to show the topology still. Or else you can also use it here. And here it is, I think it was the tortuosity that was plotted here. And you can see also again thicknesses, and you can see color codings, and that can be done with the help of this networks package if you want to look more into this graph visualization. And you can also look here with this graph analysis, you can see how many connected edges each node has, and you can draw histograms and see that we have a lot of endpoints. We have some straight connections and 3 that would be 3-way connections, and yeah, there are few nodes with 4 connections. So that also can give you an idea on the topology of this network. So that can shift depending on one side how clean your network is. If you have very many ones, that means you have a lot of mini branches, a lot of endpoints. If you have 2s, that would be more or less straight segments. And then the 3 is when it starts branching. Then you can go on and doing this in 3D. Until now I only showed it in 2D, and the 3D skeletonization is a bit more complicated algorithms, and there are also more design criteria how to build them. Some skeletons in 3D even have plates or planes as junctions. Others, they really merge down to single joints. Depends a little bit on, again, what is your criteria for your skeleton and what you need. And one application is segmenting root networks. And the motivation for looking at root networks is looking into the soil stability. Depending on how the roots are spreading out in the soil, they can stabilize the soil. Of course, it has an effect on the plant, how well it can take up water. And then one more is environmental effects. If you have microplastics or heavy metal pollution, then you can see that the root network takes different shapes. And what we want to look into in that case is, again, segment length, how much it branches, in what orientation you have your branches, and the tortuosity. And for the soil stability and water uptake, it's also interesting to look at the influence volume, because the more coverage you have from the roots, the more you can see, the more uptake it can do. And then we can have this segmented root network, which in just as it is, if you look at the single slices, you don't see much. It's just small dots everywhere. And then we can do a projection, see a little bit more how it looks like. And running the skeleton and project it, then we have a root network that looks like this. And that's still the same, but I flipped it to give more space to show it. This was the root segmentation was done using a unit machine learning, also neural network, to find the roots, because that is also not a trivial task. The skeleton is much easier in this case. And then we can look at the small details of the skeleton, and you can see that it actually represents the root structure pretty well. And with that, it's time for a break.